Folks, coming at you, recording another lecture. So as you can see by my setup here, my lecture today will be entirely on the whiteboard. So that's why I'm a little bit smaller up there in the corner, and I don't have any other documents opened. So I'm transitioning into our module on spectroscopy, and that is we're going to talk about vibrational spectroscopy, rotational spectroscopy, and more forms of electronic spectroscopy. But I want to do a crash course into statistical mechanics, StatMech. So we've had a few crash courses already in StatMech, but I wanted to specifically talk about molecular partition functions and populations of state because that's going to really help us interpret spectroscopy. So if you recall Boltzmann, okay, so we're going back, this goes way back into the 361 days, where if I have a population of molecules in state I over some total number of molecules, right, then the distribution of those populations will go e to the negative beta times eta I. I'm going to talk about this notation in a moment, divided by the sum of all states I of e to the negative beta eta I, okay? Where beta is 1 divided by k Boltzmann T, okay? So if I were to plug that in, right, this, and an eta I is energy of state I, okay? So if you plug this back in here, you would have e raised to the negative energy divided by k Boltzmann T, which you recall, that is our Boltzmann distribution. And if you think about this, if Ni is just e to the negative beta times eta, right, then the sum is just going to be the sum of all of those possible states of energy I. Excuse me. Okay, and to establish a few more quantities here, if I take the sum of all number of molecules I, that's going to give me the in total, right? And then, of course, if I take the sum of all ni's times ei's, then that gives me the total energy, okay? So if we look further into the molecular partition function now, I can change this up. So I'm going to just slightly modify this equation and write this Ni over Nt as Pi. And so that is the fractional population of molecules in state I. So it's basically Ni divided by N total, all right? And that equals e to the negative beta eta I, all divided by q, okay? Where q equals my sum of all of these other partition functions. So q is the molecular partition function q, okay? And if there are several states that exist with the same degeneracy, then this equation just gets modified slightly, and I'll say the sum of all states, I'll just use a capital I here, and now that's g of I times e to the negative beta eta I, I used a capital I, right? Where now G is my degeneracy. So in other words, if there are states that have the same energy, they're degenerate states, this is how we account for those degenerate states, okay? And so now a few things to consider with our partition functions. So by definition, if let's say the limit of Q as t approaches 0 equals g sub 0. Okay, and so as what this means, as t approaches 0, then q equals the number of degenerate states. Okay, and the limit of q as t approaches infinity equals infinity. So really what you can start to think of this partition function, it's not quite the same thing as the microstates, but you can think of it as the sum of all microstates with energy I. So it is very closely related to the number of microstates, okay? And so what we're saying here is as t approaches 0, then, excuse me, I'll make my nomenclature consistent. Oops, I'm using my wet erase pen that I forgot about. So instead of saying that that's G0, right, that's GI, this degeneracy term. So in other words, as you approach 0, this exponential drops out of the picture, and so your number of degenerate states is just your number of microstates. Your partition function really is going to give you your number of microstates at 0 Kelvin. But at infinite Kelvin, you're going to have an infinite number of states, which is similar to the connection with microstates. So again, molecular partition function, very similar to microstates. You can think of that as number of microstates. Okay? So now let's consider a system with various energy levels, and I'll draw that out here, okay? So suppose we have energy levels that are linearly spaced, so 0, eta, 2 times eta, 3 times eta, etc. Okay, so my difference in energy levels is, of course, just eta. And a good example of this is the harmonic oscillator. So the vibrations of molecules, I'll write that down, because if you recall, the harmonic oscillator model has linearly spaced energy levels. Okay, so now if we were to go to populate, or excuse me, rather take the sum of these via Q, if my bottom energy level is 0, well, anything raised to the 0 power is just 1, right? E raised to the 0 is 1, okay? So then now for my next level, this would go E to the negative beta eta. My next level would be plus E to the negative 2 times beta times eta, and so forth, right? I could keep summing up all of these, okay? And what I would find, this is actually a Maclaurin series expansion for linearly spaced only. So that's a Maclaurin series expansion. And this can be approximated as the following: 1 over 1 minus e to the negative beta eta. Okay? So what we can do here, to summarize, so I'll write Q equals 1 over 1 minus e to the negative beta eta. Okay? So if we have evenly spaced energy levels, which again, harmonic oscillator fits this model well, then instead of taking the sum of all of these levels, right, like we did with this equation, no degenerate states to think about now if all of these are evenly spaced, so no degeneracy term, then as I sum all of these up, then I could write this as a Maclaurin series expansion, and this would be a good equation for Q for any linearly spaced molecules. So effectively, that's going to give me my number of microstates of energy E, okay, with energy spacing E or eta, whatever you want to call it, okay? And so thus, if I go to rewrite my population equation right here, okay, so then I can write that now, plugging in Q and doing a little bit of algebra. That comes out to be 1 minus E to the negative beta eta. And then I'm skipping a few algebraic steps here. So this ends up being my Q, right? Okay. To the, what did I write here? 1 minus e to the negative beta eta. Yes. And then times e to the negative beta ei. Something's not sitting right with that. Let me check that for a second here. So I said my Q is 1 over that. What did I do wrong here? Oh, yes. Okay, I see what it is. Because I said that Q is 1 over this. Haha, okay. So sorry, blanking out here on my algebra. Q is 1 over this function, right? So if I take 1 over this function, I just get the 1 minus e to the negative beta eta times e to the negative beta ei. Okay, great. So then here is my population equation. Okay. So let's see. I'm going to leave these two equations down here, and I'm going to attempt to erase everything else with my wet erase marker. And then I'm going to do some sample calculations for you. Okay. Actually, I might just have to erase everything. We'll make this easier for stuff. Okay. As you know, I like to use this wet erase marker because it writes better, but it takes me some time to erase this stuff, and I'm going to get marker all over my hands. That's cool. Okay. Okay, great. So, a few calculations to do. So let me rewrite my equations that we came up with. So we said my population of any state I, where there's linearly spaced energy levels, goes as the following. Okay. E to the negative beta eta I. Okay, great. I think there's still some methanol solution in there, but that's all right. Okay, so now a few things to consider. Let's talk about this value of beta, this 1 over kBt. Because as it turns out, the value of this beta equation is pretty important. This is bugging me now. I'm going to erase this because I think there's still some marker, some erase solution right there. Okay, 1 minus e. Okay, and then times e to the negative beta eta e I. Okay, so remember, that's the energy of level 1, and that's the energy difference between the two levels. Okay, so now the value of kBt. So as it turns out, K Boltzmann T at room temperature at 298 K equals 4.116 times 10 to the negative 21 joules, which is the same as 0.0257 electron volts, or in other words, 25.7 milli electron volts. So I want you to keep this in mind. kBt at room temperature is 25.7 milli electron volts. Why is that important? We're going to get there. And now we could also think of this in terms of wave numbers. And as it turns out, this energy is also 207.22 wave number. And I'll show you how we do that. Recall, anything that I want to convert to a wave number, I just simply divide by HC. Okay? So K Boltzmann 1.23, I think, 1.38 rather. Okay? 1.38 times 10 to the negative 23 joules per Kelvin times 298 Kelvin divided by 6.626 times 10 negative 34 joules seconds times 2.998 times 10 to the 8 meters per second. Okay, look, Kelvin and Kelvin cancel. Joule and joule cancel. Second and second cancel. And what I get when I do this calculation, you get 207.22 over meters. So 20,722 over meters. And then times, in 1 meter, there's 100 centimeters. that gives me 207.22 wave number. Okay, so that's how I get that. So kBT at room temperature, about 4 times 10 minus 21 joules, which is about 25 milli-electron volts, which is 207 wave numbers. Here's where this is going to be important. In general, when something has an energy spacing, when something has an energy level, look at how we're doing this, right? It's the energy level times beta, okay? And then raised to the power E. So when our energy level is close to this value beta, we're going to have something like, a population that's 1 minus E raised to the 1. So when energies are in this level, what that basically means is almost all of your population, when you have energies that are greater than this value, you're basically only going to have one state populated. I'm going to give you an example of that. So suppose we want to calculate, so suppose we have molecule okay, and I'll use some different colors so we can see some things. We have molecule AB, okay? And it has a vibrational energy of, let's say that its new tilde value is 2,000 wave numbers. So the energy, so the vibration of that AB vibration is about 2,000 wave numbers. So maybe it's like a carbonyl or something like that, okay? So what would the population of AB be in its first excited state at room temperature, okay? So I'll ask that question again. What would be the population of AB in its ground state? So let's say population in ground state and first excited state at 298K. Okay. So here's how we calculate it. The first thing we would want to do is calculate population 0. So that's going to be, so P0 is the ground state, and P1 would be the first excited state. So P0 is going to go 1 minus E. And so look, that's beta times eta. So remember, kBT is 207 wave number. Beta is 1 over that. And consider that if we're using energy in wave numbers, if my eta value is in wave numbers, I want my beta value to also be in wave numbers. If my eta value is in joules, then I want my beta value also to be in joules. All right? So now I'm using this 2,000 wave number as my value of energy, right? So now what I have is I'm going to fill out this equation right here, okay? 1 minus E to the negative. So that eta value, that's the 2,000 wave number. And it's going to be divided by kBT. Because remember, beta is 1 over kBT. So that's 207.22 wave number. And now I have to say, let's see, E times, and then what's missing from here, what I didn't write in my equation, let's see, where did I miss writing that down? Yes, because the energy level, the ground state, we said, starts at 0. This whole thing is going to be E to the negative 0, okay, which basically drops that down to 1. So for this ground state level, I only have to consider this equation right here, all right? And if I go and calculate that, okay, so excuse me, let me fill this out more correctly for future calculations. All right, I think somewhere I didn't notate this. When I did that sum for Maclaurin, right, consider that what we want to have is also, let's see, how can I notate this better? Okay, well, what I would want to do over here is say e to the 0 times, and then that's going to be negative 2000 wave number divided by 207.22 wave number. And you can see that 0 is going to make this whole thing go to 1, but that's going to be important for my future calculations. So this whole chunk equals 1, and this whole chunk, when you calculate it, equals 0.9999 1, 2, 3, 4 nines 36. Okay? So in other words, the population of my ground state, if something has an energy of 2000 wave number at 298 Kelvin, my ground state has basically 99.99% of all the molecules. All right? So P0 equals, let's say 99.9936%. Well, now what about P1? So it's tempting to say, well, just 1 minus that, but you have to consider you also have a population of the upper lying levels as well. So when I go to calculate P1 now, all right, that's going to be 1 minus e to the negative 2000 wave number divided by 207.22 wave number, right? But now that's going to be times e to the 1 times negative 2000 wave number divided by 207.22 wave number. So I put my little population, or my level, right there. Okay? And so I know that this all equals 0.999936. But now when I go and calculate this, let's see, this is 0.000064264, and basically when I take this times this, it effectively gives me nearly this same number. So my P1 ends up being, let's see, we'll call it 6426 with the significant digits. So 1, 2, so it ends up being 0.00646%. So effectively, 1 minus this, you can see those add up nearly to 100%. But if we were doing this correct, we also have to consider there technically would be a very, very, very incredibly small population for level 2 and level 3 and so on. Okay? And so this kind of makes sense based on what we observe in vibrational energy. So we talked about this already, that everything is in the ground state. Nearly everything is in the ground state for vibrations. And that's what we just proved. So if I have molecule AB and it has a 2000 wave number stretch, and this is like without even giving it extra energy, right? We're not even shining IR light on this thing. This is just how molecule AB will exist at room temperature. 99.99% of everything will be in the ground state, and a very, very small fraction of things will be in an upper lying state. And if we redo this calculation, so I'm not going to go through and do another calculation, but I'll just give you the results. So suppose now, okay, let's see if I can do this. So suppose now, instead of 2000 wave numbers, let's get rid of all the 2000 wave numbers here. And so we can calculate a new one. Okay, kind of, something like that. Suppose it was a 500 wave number stretch instead, so much lower in energy. And as you can see, approaching that 200 wave number value. So that's what I want here. I'm approaching that value of K Boltzmann T. So now I would plug in, 500, 500, and 500. And so when I do that, I no longer get these numbers, right? These numbers are all going to change, of course. And you can kind of predict what's going to happen. You can start to think about it. Okay? But now, sorry, this is kind of sloppy looking, but now if the energy is 500 wave numbers, as it turns out, the population of the ground state actually goes to 91.047%, and the excited state goes to 8.152%. Okay? So, what we see here, I'll write an important thing to note here. So I'll get rid of all of this. And, you can see the math is, once you know how to use the equations, assuming that you've got the equations written down correctly, the concept that I want you to get out of this is the following. So as your value of energy, as eta approaches that of beta, okay, let's see, how can I write this? Your ground state population is going to tend to values less than 1. Okay? But as eta gets much bigger than the value of beta, then your population is going to be virtually equal to 1. Okay? So this is the case with vibrations, as we just shown. It's also the case with electronic transitions. Over here, this is the case with rotations. So rotational energies, and really I said as E approaches beta, but a better way to write this would be as E becomes less than or even equal to beta, okay, on par with the value of beta. This really is applying to rotations and translations. All right. And so to give you a value, to give you an idea of this, the value of Q for that 2,000 wave number stretch, and remember Q is just 1 over 1 minus E to the negative beta eta, okay? So that is 1.000064. But the Q at 500 wave numbers, just the value of Q, was 1.09833. So the idea behind this, as this Q is really approaching 1, and so I'll put another thing on here, Q approaches 1, but over here, Q is going to be much greater than 1, all right? And what that shows you is this reflects a much smaller spread in population, or this reflects a spread in population where this reflects no spread in population. So no spread at all. And here the population is more spread out. It's more distributed between the states. So again, when you have an energy level that's much less than the value of beta, and keep in mind, beta is 207 wave numbers. That's why this really follows for rotations and translations, much more than vibrations or electronic transitions. It kind of predicts exactly what we've been saying, that at room temperature, you expect all molecules to exist in their ground vibrational state and their ground electronic state. But at room temperature, molecules will have a spread of populations in their rotation and a spread of populations in their translational states. All right? So I'm just going to now draw up the equations for each one of these states specifically, so we can get like really, really specific with these equations for electronic vibrations and rotations and translations. I'm not going to hold you responsible for deriving them or anything, but I am just going to present those equations for you. Let me get this board nice and dry. Okay, so to summarize our partition functions. Okay, let's see, let me write the translational partition function. I'll just say PF for partition function. Okay, So I'm just going to give you the function directly. So it goes as, let's see here, Q, and we put a superscript T for translation. And I'm just going to present it. So it ends up going as the following. V divided by lambda cubed, where V is the volume of the system in question. And this lambda cubed is called the thermal wavelength. So that's thermal wavelength, and thermal meaning the de Broglie wavelength. And that lambda equation is equal to H divided by the root of 2 pi mk Boltzmann T. 2 pi mk Boltzmann T. Okay? And so I'll give you an example. So QT, the value of QT for H2 in a 100 cubic centimeter box equals 2.77 times 10 to the 26th power. So now what does that mean? So effectively what that tells you is there's 2.77 times 10 to the 26 microstates available for an H2 translating in a 100 cubic centimeter box. And so if you recall, what we said was as the energy level gets much less than the value of beta, the value of Q greatly increases from 1. And that indicates a huge spread in population. And indeed, right, if you recall from our Maxwell-Boltzmann distribution of velocities, we have a huge spread in the different types of velocities. So this makes sense for translations. Okay? If we look at our rotation partition function, okay, that goes as QR for rotation. And I'll just write the equation down for you directly. It goes the sum of all J, and this is the rotational quantum number J. Don't get this confused with another letter J. This is rotational quantum number that we're going to talk about soon. And that's E to the negative beta times HC times B tilde times J plus 1. So what is all this stuff? Well, all of this stuff right here is the value of eta in wave numbers for rotations. Okay, and we're going to get there. We're going to talk about this soon. But here's the function. And so what you can see then is this 2j plus 1 is my degeneracy. Okay, so that's my G of I degeneracy. And we're going to come back and see where all these equations come from. All right? And so now if I go and look at my vibrational partition function, let's see, QV, okay, that equals the sum of all nus, so that's my vibrational quantum number nu, right? E to the negative beta times HC times nu tilde times nu. So this is quantum number. And you recall in that example that we just calculated, right? When I did the ground state, that value is equal to 0, right? So 0, 1, 2, 3, etc., depending on the excited state level. This nu tilde right here, so that's the value of eta in wave numbers. Okay? And then finally, let's see, my electronic partition function goes as the following. Q, capital E, equals the sum of all quantum number n, so that's principal quantum number n. And actually, let me say over here really quick, right? J is going to be equal to 1, 2, 3, 4, etc. And we'll talk about that J in a minute. We've talked about n. We've talked about principal quantum number n already. And so this goes as G lowercase j, too many j's, too many letters. Okay. Okay, so then now, this one's a little bit more straightforward. So this is just the value in joules or wave numbers or whatever if you like. But now this lowercase j, this is for the quantum number L plus quantum number S, all the way down to quantum number L minus quantum number S. Okay, so you just have to keep track of all of these quantum numbers depending on what system we're talking about. If we're talking about electronic quantum numbers, vibrational quantum numbers, rotational quantum numbers, etc. And then now for my total molecular partition function, if let's say I wanted to know the total number of microstates at a given energy. So my total energy, right, is going to be the E of state I for translations, the E of state I for rotations, vibrations, and electronic transitions. Okay? And because my partition function is always a sum of all states, right? Then effectively what I get is when I sum all of these together, let's see, so I can sum it over all states. I hope I have enough room here. So that's going to be e to the negative beta eta t minus beta eta r minus beta eta v minus beta eta e. Right? So it's going to be the sum of all of those things. Or another way to write this would be to break down the sum of each one. And then we know with the property of exponentials, we can actually just write these as a product. So Q total is just going to equal the product of all Q's, which basically equals QT times QR times QV times QE. And what's important to note for the QV and QE state, remember from our previous calculation, QV, we calculated that, right? It's basically equal to 1. QE is also going to be equal to 1 because of the fact that the vibrational and electronic energies are so much greater than the value of beta, right? We expect everything to be in their ground state for vibrations and electronic transitions. So really the total molecular partition function is almost entirely dependent on translations. Again, because if you think about this, the QT for H2 in a 100 cubic centimeter box is 2.77 times 10 to the 26th power. So as far as like all of those microstates are concerned and how this relates to spectroscopy, translations and rotations, it's quite important. Vibrations and electronic transitions, it's not really important at all unless you're at really, really high temperatures. Okay. So once again, moral of the story, at room temperature, everything in the electronic and vibration energy levels is in the ground state. Everything is in the ground state. Okay. For rotations and translations, there's a huge distribution of population, and our microstates that we associate with entropy and thermodynamics is almost entirely from the translations of molecules. Okay, folks, so this was a little crash course in the STETMEC and partition functions. The next lectures will deal with, we're going to go with spectroscopies in order of increasing energy. So I'm going to start with rotation and then go to vibration and then go to electronic transitions. And so with our rotational partition function, there's a lot of all of this stuff we talked about that we're going to have to consider. But as we get to vibrational and electronic spectroscopies, we're not going to really have to consider this much at all. All right, folks, I'll see you in the next video.